When mixing two or more chemicals, one may wonder whether a chemical reaction would take place between them. Some chemicals, when put together, will react to form products of identity different from their own. Sometimes, even one chemical left by itself will undergo a spontaneous chemical change. Other chemicals, by their very nature, are incapable of reacting with each other under any circumstances. There are criteria which allow us to determine whether there would or would not be a reaction between chemical species, even without carrying out of an experiment. For this reason, we can use data from handbooks of chemistry and physics. These criteria will be the subject of another lecture. There are numerous instances whereby reactions can take place, but their procedure is so slow, that is, the products of these reactions are created so slowly, that for all practical purposes these reactions are useless. Indeed, what will be the use of a reaction whose products would appear in, say, 100 years from now? Thus, the question regarding the rate of a chemical reaction has a significance comparable to the very possibility of a chemical reaction to occur. The area of physical chemistry that studies rates of chemical reactions and methods to control these rates is called chemical kinetics. Although the methods of chemical kinetics can be very involved mathematically and physically, and can be very challenging intellectually, the results of applying these methods may have enormous practical applications. The formal mathematical description of the rate of the reactions, without taking into account their mechanism, is the subject of the so-called formal kinetics. A more essential part of chemical kinetics is the study of the mechanism of interaction between the separate molecules, and this area encompasses the theory of collisions and the theory of transition state. Now, a difference should be made between mechanism of interaction between the separate molecules and mechanism of the reaction as a whole. Under mechanism of a reaction, here, one understands the totality of all its stages. Some reactions can proceed in only one stage, and they are called simple reactions. These reactions will be in our main focus of attention. The complex reactions, consisting of more than one stage, can be serial, parallel, conjugate, chain, and reversible. Chemical reactions that consist of stages proceeding consecutively one after another are called serial reactions. For instance, if the substance A reacts with the substance B and forms a product X, and then the same substance A reacts with the product X to form a product Y, then we will have a serial reaction. And if the first stage is slow, while the second fast, then this first stage is called the rate determining stage, or the rate determining step. A good analogy for the rate determining step in serial reactions is the flow of fluid through the narrowest section of a tube. Indeed, the overall rate of flow of this fluid will be determined by the rate of flow through this narrowest section, sometimes called bottleneck section. When the limiting stage, or the rate determining step of the reaction, is the very chemical interaction of species, then we say that the overall reaction is under kinetic control. If, however, the limiting stage, or the rate determining step, is a transport of the reacting species to the region where the chemical interaction occurs, then we say that the chemical reaction, the overall chemical reaction, is under diffusion control. Chemical reactions can also be under mixed control, when the rate of transport of the reacting substances to the region where the chemical interaction occurs is commensurate with the chemical interaction, with the rate of the chemical interaction itself. Complex reactions consisting of elementary steps, elementary acts proceeding in parallel are called parallel reactions. In parallel reactions, the chemical interaction between the same initial reactants leads to the formation of different products. The overall rate of a parallel reaction is determined by the rate of the fastest stage. For parallel reactions, the analogy of fluid flowing through tubes again comes in handy to illustrate that indeed the fastest route is the rate determining. Of course, complex reactions can be combinations of serial and parallel reactions, and also there can be some more exotic types of complex reactions, such as conjugate reactions, for instance, whereby one reaction takes place spontaneously, while another reaction can take place only if there was the first reaction. An important type of complex chemical reactions are the so-called reversible reactions. In principle, all chemical reactions are reversible in chemical sense, meaning that the reactants can be restored from the products. In many instances, the rate of the reverse reaction is comparable to the rate of the forward reaction and cannot be neglected in the analysis. Therefore, the analysis of such complex reactions must include both the forward and the reverse reaction. These opposing arrows indicate that the reaction is reversible. Many of the chemical reactions we're going to observe proceed practically to completion. That is, when chemical equilibrium is reached, the concentration of reactants is negligible compared to the concentration of the products. Reactions at which one or more products leave the phase in which the reaction takes place are usually irreversible. For instance, in solutions, when at least one of the products is being obtained as a precipitate, or is a gas, or if a weakly dissociating substance is obtained. Exothermic reactions of high heat effect are also practically irreversible. Thus, when observing such reactions, it is acceptable to analyze only the forward reaction, and of course, this reaction is irreversible in thermodynamic sense. In many instances, however, the rate of the reverse reaction cannot be neglected, and the analysis must include both the forward and the reverse reaction. Now we'll digress for a moment to comment on chemical versus thermodynamic reversibility. It should be clear that chemical reversibility can be considered also a thermodynamic reversibility only in cases when the chemical reaction has reached a point whereby the rate of the forward reaction equals the rate of the reverse reaction. In other words, only chemical reactions that have reached chemical equilibrium can be considered reversible in thermodynamic sense also. A chemical reaction proceeding at a point far removed from the chemical equilibrium cannot be considered thermodynamically reversible. It is also chemically irreversible in the sense that we can only consider the forward process. Thus, when observing chemical reactions proceeding to completion, it is acceptable, as already noted, to analyze only the forward reaction. And of course, this reaction is thermodynamically irreversible. Connected with this clarification is the use of the concept thermodynamically reversible process. A thermodynamically reversible process can only be a process that is due to an infinitely small difference between the rates of the forward and the reverse reactions. In other words, a reversible process is an infinitely slow process, and it takes place when the system's deviation from equilibrium is infinitely small. When the system is far removed from equilibrium, the process is always an irreversible thermodynamic process. We used already, not once, the term rate of a reaction. What is rate of a chemical reaction, indeed? Study of chemical kinetics starts with one very natural definition for the rate of a reaction. Rate, in principle, is the change of a parameter per unit time. In chemistry, in chemical kinetics, rate of a reaction is defined as the change of the concentration of the reacting substance per unit time. For a reaction of simple stoichiometry, with stoichiometric coefficients unity, the average rate of the reaction for the time period delta t is determined by the ratio of the change of the concentrations of any one of these participants in the reaction over the value of the time period. The rate of a chemical reaction, the average rate in this case, is always expressed by a positive number. Therefore, we have to be careful when we use the change of the concentration of the reactants in this definition. Concentration of the reactants decreases in the course of time. Therefore, the concentration of the reactant, for instance A, at the end of the time period is lower than the concentration of the same reactant at the beginning of the period. Therefore, the numerator will be a negative quantity. The denominator is a positive quantity, therefore the whole ratio becomes a negative quantity. To make it positive, we have to multiply it by -1. Obviously, if we use the change of concentration of the products, say of the product X, in this definition, we do not have to multiply by -1. Concentration of X at the end of the time period is larger than the concentration of X at the beginning of the time period. When the time period delta t becomes infinitely small, the limit of this ratio is the first derivative of the concentration of the reactant, in this case reactant A, over t, over time. This first derivative represents the so-called momentary or instantaneous rate of the reaction, or the rate of the reaction at moment t. In other words, this is the value of the slope at time t of the function of the concentration of reactant A versus time. Of course, this is also the slope at time t of product X concentration as a function of time. And this is a symmetrical curve. Unfortunately, above definition of the rate of reaction provides an expression only for the momentary rate, as already mentioned. Usually, however, the reaction rate changes in time, and this changing nature of the reaction rate should be expressed in a form that would account for the changes that occur among the participating species during the procedure of the reaction. Therefore, we need an additional approach that would allow us to express the rate of the chemical reaction in terms of parameters characteristic of a chemical reaction. One natural road to go along is to establish experimentally the dependence between the rate of the reaction and the molarities of the species A, B, X, Y, and sometimes even species that don't participate in the net equation. And then once we have this experimental dependence, we can approximate it by an analytical function f. So we may write rate of the reaction equals, this is the function of the molarities of the participating in the net equation species. And sometimes even species that don't participate in the net equation. If the rate of the reaction depends on species that are not in the overall, in the net equation, these species are called catalysts. If these species decrease the rate of the reaction, they are called inhibitors, usually. If indeed an analytical expression can be found that would fit the experimental data for the rate of the reaction, then a differential equation of this type can be constructed, whose solutions will give the dependence of the concentration of the given species, species A in this instance, as a function of time. If indeed an analytical expression of a function can be found that would fit the experimental data for the rate of the reaction, then a differential equation of this type can be constructed, whose solutions will represent the change of the concentration of the given species, species A in this case, in the course of the reaction. As it is obvious from our discussion so far, it is very desirable to know the solutions of this differential equation. For instance, it is very desirable to know how the concentration of species A depends on time. In this way, we will be in a position to predict the outcome of the reaction at any moment. The form of this function f many times can be somewhat complicated, and yet common features have been established between the ostensibly different types of reactions. Thus, some simple differential equations can be constructed, whose solutions are easy to determine, as we will see shortly. The approach to find these commonalities between the various chemical reactions is as follows. In chemical kinetics, from the beginning of its development, it has been proceeded from the natural supposition that only molecules which meet, only molecules which collide with each other can react, and the number of collisions between the molecules is proportional to their concentration. Therefore, a simple conclusion can be drawn that the number of reacting molecules per unit time, respectively the rate of the reaction, should be proportional to the concentration of the reacting molecules. Thus, if this is the overall equation of some general type of chemical reaction, where the small letters denote the stoichiometric coefficients before the reactants, respectively the products, then the rate of this reaction many times can be given by this simple expression, in which by K we have denoted the so-called rate constant of the reaction. A and B in brackets are the molarities, of course, and the exponents m and n have a significance which will become clear shortly. This expression, which is usually called kinetic equation of the reaction or law of mass action, is a basic postulate of chemical kinetics. This is one of the remarkable discoveries of chemical kinetics. The fact that out of so many possible forms that functions may have in principle, the form of the function that best fits the rate of most chemical equations is simply the product of species concentration raised to a certain power, is a remarkable achievement. As is seen, when the concentration of species A and B is equal to unity, the rate of the reaction is equal to the rate constant. Rate constant is also called specific rate of the reaction. Speaking of colliding between molecules, it would appear that we can fully characterize a chemical reaction by indicating the number of particles, molecules, atoms, ions, radicals, which participate simultaneously in the elementary act of this reaction. That is, by determining the so-called molecularity of the reaction. That is, the number of molecules simultaneously colliding with one another during the elementary act of the chemical reaction. Reactions which take place through the simultaneous participation of 1, 2, or 3 particles are called respectively monomolecular, bimolecular, and trimolecular. If more than 3 particles participate in the reaction, it does not take place in one single act, but is a complex reaction and consists of several elementary stages, which on their part are monomolecular, bimolecular, and in very rare cases trimolecular. This is so because the simultaneous collision, even only between 3 molecules, is a very low probability, and trimolecular reactions are encountered very seldom. A simultaneous encounter of more than 3 molecules is a practically impossible event, and reactions of high molecularity practically do not exist. Unfortunately, the overall chemical equation, which one might think would be a good basis to judge for the molecularity of a reaction, actually seldom represents the number of molecules simultaneously colliding. Observe, for instance, the equation shown here. According to this overall equation, there must be 13 molecules colliding at once. This, of course, is physically impossible. Therefore, one cannot judge from the overall equation the molecularity of this reaction. Complex reactions, such as the one just discussed, proceed in many steps, each step involving the simultaneous encounter of much fewer number of particles, maximum 3 as mentioned. In other words, the mechanism of these complex reactions is more complicated than is seen in the overall equation. Thus, for complex reactions, similar to the one just observed, which constitute many if not most of the chemical reactions, molecularity is an inconvenient way to characterize chemical reactions. A better way to characterize chemical reactions, at least many of the more common reactions, is by using the exponents in the kinetic equation. The sum of the exponents, in this case m plus n, comprises the so-called overall order of the reaction. In other words, the order is given by the number of particles, molecules, whose concentrations, or partial pressures, determine the rate of the reaction. One can speak also of partial order of a reaction with respect to a given species, given molecule. For instance, in this case, the partial order of the reaction with respect to species A is equal to m. Notice also that the order of the reaction is always defined in terms of reactant concentrations. Many chemical reactions have an order which makes their analytical description in mathematical terms convenient. There are reactions of zeroth, first, second, third, as well as of fractional order. We will observe examples of such reactions shortly. Unfortunately, not all chemical reactions have an order. For instance, the classical example of the reaction between hydrogen and bromine shows that the analytical function that fits the experimental data for the rate of the reaction has a more complex form. In this function we even see the participation of the product, hydrogen bromide. Heterogeneous reactions usually have more complicated kinetic equations. Here are some examples of catalytic reactions. This is the reaction of sulfur dioxide and oxygen on platinum catalyst. We can see in its kinetic equation the product sulfur trioxide participates. Also the decomposition of dinitrogen oxide on platinum at 741 degrees centigrade. Again, somewhat more complicated kinetic equation. Sometimes simplifying conditions can be found which turn the kinetic equation into a form much easier to work with. For instance, the rate of reactions catalyzed by enzymes is represented by this form of the kinetic equation, where S is the substrate, that is, the species undergoing the reaction. If the concentration of the substrate is much greater than K prime, then this complicated form of the kinetic equation turns into a form of the kinetic equation describing reactions of zeroth order. On the other hand, if the concentration of the substrate is much smaller than K prime, then the rate of the reaction is described by an equation of the first order reaction. For simple reactions, that is, reactions consisting of only one stage, the order and molecularity may coincide. In other words, the form of the rate law, the form of the kinetic equation that is, may coincide with the form which would be expected from the stoichiometry of the reaction. For instance, the oxidation of nitrogen oxide takes place in one stage and is described by a kinetic equation, by a rate law, which corresponds to a reaction of third order. It is seen that order of 3 corresponds to the sum of the stoichiometric coefficients in the overall equation of this reaction. In most cases, however, as already mentioned, the reactions are complex. That is, they consist of several stages. They include several elementary acts. The rate of these complex reactions is determined by the rate of the slowest stage, if these stages are sequential, which also determines the order of the reaction. Thus, only in very rare cases does the order of the reaction coincide with the sum of the stoichiometric coefficients in the equation of the reaction. That is, very seldom does the order of a reaction coincide with the molecularity, which the reaction would have if it would consist of one stage. The exponents of the concentrations in the kinetic equation usually do not coincide with the stoichiometric coefficients. For instance, the reaction of thermal decomposition of dinitrogen pentoxide is expected to be of second order due to stoichiometry. However, experiment shows that in fact it is of first order. As it is seen, there is a fundamental difference between molecularity and the order of a reaction. Molecularity is determined by the actual number of molecules which interact simultaneously upon encounter. Evidently, the molecularity cannot be zeroth or fractional, while the order of the reaction is a purely formal quantity, determined by the exponents of the concentrations in the equation of the rate law, the kinetic equation. Before going further, here's the promised commentary on expressing the rate of a reaction having more complex stoichiometry. Suppose, for instance, that we have the following hypothetical reaction. A plus 3B gives 2X. Then we can express the rate of this reaction using the change of the number of moles of species A. We can write Ra equals minus dNA. This is the number of moles of species A, dt. Now, if we want to express the rate of this reaction by the change of the number of moles of species B, we can write Rb equals minus dNb dt. However, this will be equal to 3 times Ra. If we want to avoid this ambiguity and express the rate of the reaction as the change of the number of moles per unit time of any one of these participants in the equation, we have to divide these expressions by the corresponding stoichiometric coefficients. Here we see the same expression rewritten. Now, if during the reaction the volume doesn't change, we may divide by the volume. And because dNA over V equals change of molarity of species A, we can write this chain equality using the same letter R for the rate of the chemical reaction. For a reaction of general type, shown here, where the small letters denote the stoichiometric coefficients, and provided there are no intermediates formed during the reaction, the rate of the reaction is expressed by this chain equality. Notice that if intermediates are formed and the reaction has not reached equilibrium, these equalities may not be true, because at such conditions the rate of turning of reactants into intermediates may be greater than the rate of turning of intermediates into products. Before proceeding with the integration of some simple differential equations describing reactions of different orders, we will mention a few words about the methods for experimental determination of reaction rates. Although these methods can sometimes be a matter of great inventiveness and sometimes require special experimental skills on the side of the researcher, probably they can be placed in mainly 2 categories, dynamic and static. A dynamic method may consist in the following. The reacting substances, gases, are placed in the reaction zone at a given rate, where a sufficiently high constant temperature is maintained. From the reaction zone, they come out fast and get into a zone of low temperature, where tempering takes place and the reaction is ceased. By determination of the quantity of the reacting substance and the time of stay in the mixture in the reaction zone, one can calculate the rate of the reaction at the given temperature. A static method may be the following. The time change of the concentration is measured of the reacting substances without placing in and taking out of the mixture. Usually, the change of the concentration of one reactant is observed, while the rest of the reactants are held in excess. In this way, usually a rate law of pseudo-first, pseudo-second, and so on order with respect to that reactant is obtained. We will make a slight change in notation now. Instead of writing the concentration in square brackets, we will use a small letter C. In this way it will be easier to write equations, and this will make them more general. Besides, changing of the symbol will not change the meaning of the quantity. We will begin the study of differential equations, which describe the rates of various chemical reactions, by first observing irreversible chemical reactions. That is, reactions in which the rate of the reverse reaction can be considered negligibly small. Now let's observe some simple differential equations connected with reactions of various orders. Let's start with the simplest type, reactions of 0th order. These are reactions of the type A leading to products X. The rate of such reactions, which is dC dt, is constant, does not depend on the concentration of the species. Integration of this differential equation is pretty straightforward. We'll separate the dependent from the independent variable. And then we'll integrate from concentration or vapor pressure C0 to C, and from time T0 to time T. Both sides of the equality are integrated within these boundaries C0 to C and T0 to T, and the definite integrals are evaluated here. Of course, we could have integrated it with indefinite integral. We'll do this later in other examples. And here is the outcome of the integration. Rearrangement of the last expression gives this function as the solution of the differential equation, and this is a linear dependence between the concentration of species A as a function of time. The intercept is equal to C0, and the slope of this line is equal to minus K0. It is obvious that this expression will hold for times t lower or equal to C0 over K0. Recall, C0 is the initial concentration of the species A, K0 is the rate constant. For times greater than this ratio, the solution of the differential equation will be C equals to 0, and this is very natural because there will be no more species A at times greater than this ratio. Here again are the solutions to the differential equation describing zeroth order reactions. Now it's interesting to see what the so-called half-life of this reaction is. Half-life of a reaction is the time required for the initial amount of the reacting species A to decrease in half. Although the answer to this question may be considered trivial, we'll observe it because of the methodology which we will apply later too. Thus, we will substitute in the solution of the differential equation C0 over 2 equals to minus KT, T, 1/2, this is half-life, plus C0. This, the half-life T 1/2, is equal to 1/2 of C0 over K0. Indeed, it is trivial. If the entire amount of this reacting species A disappears for time C0 over K0, then half of this amount will disappear for half of this time, 1/2 of C0 over K0. Again, what we did to find the half-life was the following. We substituted in the solution of the differential equation for C the value of the half initial concentration of the species A. And then we obtained this expression. Then we solved this expression for the half-life and obtained 1 over 2 C0 over K0. As it is seen from the differential equation, the dimensions of the rate constant for a zeroth order reaction are mole per liter to the minus first per second to the minus first. Of zeroth order are, for instance, some reactions in solution at which the substance of limited solubility taking place in the reaction is taken in excess, and its expenditure during the reaction is compensated continuously through its dissolution. Also, catalytic reactions can be of zeroth order with regard to the catalyst. The rate constant K0, however, may depend on the concentration of the catalyst. K0 also may depend on the intensity of light with photochemical reactions. Many heterogeneous reactions are of zeroth order. Here is an example of one such reaction. Fractional order is usually observed with reactions that are realized through more than one elementary acts. For instance, the decomposition of acetaldehyde. The rate of the reaction is represented by this rate law. The decomposition of ozone, catalyzed by dinitrogen pentoxide, is also represented by a rate law indicating a fractional order of the reaction. The rate of a first order reaction is proportional to the concentration of the reactant. By K1, which is the coefficient of proportionality, we denote the rate constant of first order reactions. We can solve this differential equation by the method of separation of variables. Now we can integrate both sides of this equality. This is an indefinite integral. The last line is rewritten here. Of course, we may multiply both sides of the equality by -1. Then we observe that by the rules of derivatives, dc over c is in fact d logarithm of c, integral, minus k1. K1 was taken out of the integral because this is a constant, integral of dt. The result of the integration is logarithm of c equals minus k1 times t. And because these are indefinite integrals, each one of them yields one arbitrary constant. We'll consolidate these two constants into one common constant on the right side of the equation, whose value is now to be determined. The value of the constant is determined by considering that at time t0, the concentration of the reactant is equal to the initial concentration, C0. For time t0, the form of this expression becomes logarithm of C0 equals 0 plus constant. From where we see that the value of the constant is equal to logarithm of C0. We have replaced the value of the constant in this expression. We can rewrite the expression as logarithm of c equals logarithm of c0 minus k1 times t. And we can take the anti-logarithm of both sides of this equality. Thus we obtain c equals c0 times e to the minus k1 t. By the way, we can evaluate the first order rate constant k1 from this expression, and we write k1 times t equals logarithm of c0 minus logarithm of c equals logarithm of c0 over c, from where we have k1 equals logarithm of c0 over c divided by t, which is also 1 over t, logarithm of c0 over c. From this expression, we see that the rate constant k1 is expressed in seconds to the minus first. Thus we see that the concentration of the reactant during the course of a first order reaction is an exponential function of time. We can also express the solution of this differential equation in terms of the concentration of the product. We can plot the exponential decrease in time of the concentration of the reactant, as well as the exponential increase in time of the concentration of the product. At the point of intersection of these two curves, we have the condition C equals x, or C0 minus x equals x, from where x equals C0 over 2. In other words, at the intersecting point, the concentration, the initial concentration of the reactant has decreased in half. The time that corresponds to this point, as we already know, is called half-life. Analytical expression for the half-life of a first-order reaction can be found from the solution of the differential equation by substituting the value of the half initial concentration in the place of C in this solution. Thus we obtain 1/2, or 1/2 equals e to the minus k1 t 1/2. Of course, we can take logarithm of both sides of this equality, and then we'll have logarithm 1/2 equals minus k1 t 1/2. From here, we can express the half-life. And this is t 1/2 equals minus logarithm of 1/2 over k1. And then we'll have 2 1/2 equals minus logarithm of 1 over k1 minus logarithm of 2 over k1. Now this is 0. This is t 1/2 equals logarithm of 2 over k1, which is 0.693 over k1. As is seen from this expression, the half-life of first-order reactions does not depend on the initial concentration of the reactant. And this is very easily explained by the fact that the reaction of each one individual molecule is spontaneous and does not depend on the presence or on the state of other molecules. Here are some examples of first-order chemical reactions. Decomposition of azomethane, decomposition of dinitrogen pentoxide, decomposition of dimethyl ether. Also, some non-chemical processes can display characteristics of first-order kinetics. For instance, radioactive disintegration follows first-order kinetics, and the half-lives of radionuclides, that is, the radioactive isotopes, do not depend on the amount of the radioactive substance present. Indeed, the radioactive disintegration is due to intrinsic causes within the nucleus of the atom, and no chemical or physical changes such as change of temperature or pressure can influence its procedure. As a matter of fact, half-life and not rate constant is one characteristic by which different isotopes are distinguished from one another. When referred to a radionuclide, the rate constants are called decay constants. We will see now what the mean probable life of one separate molecule with the reactions of first order is equal to. Similar to the already observed differential equation, we can write minus dn dt equals k1 n, where n is the number of molecules at time t. We already know what the solution of this type of differential equation is, so we write n equals n0 t. We can take a differential of both sides of this equality. Dn equals minus k1 n0 minus k1 dt. Once we have the expression for dn, where n0 is the number of molecules at time 0, we can substitute it in the expression for the mean time. 0 to infinity t dn over n0. And now, of course, We can cancel out and 0. And what remains is an integral which is to be solved. We immediately see that minus k1 times the exponent can be placed under the differential. This integral can be easily solved through the integration by parts. And here we solve the integral through integration by parts. We have symbolically integral of u dv is equal to uv minus integral of v du. From the table of integrals, it is easily seen that this integral is equal to integral of differential of this expression, which of course is equal to the following. And we immediately see that this term in the expression is 0 both at the lower and the upper bound, while this term is 0 only at the upper bound, while at the lower bound this exponent is equal to unity. Therefore, the mean probable life of one molecule in first order reaction is equal to the reciprocal value of the rate constant of first order reaction. Now, one short comment about the definition of mean probable life of one single molecule. There's nothing mysterious about this formula. Here dn is the number of molecules that have survived until time t. We can form these products of t dn. This is the time, the total time of survival of these dn molecules. Then we can sum up for all times and we can obtain this total time of survival of all molecules. And this total time we can divide by the initial number of molecules at time 0 to obtain the average time of survival, average time of existence of one single molecule. Let us observe now the formal kinetics regarding reactions of second order. This is symbolically the equation of a reaction of second order. In studying these reactions, there may be two cases. The first case is when the initial concentrations of the reactants are equal to one another, and the second case is when the initial concentrations of the reactants differ from each other. In the first case, the kinetic equation, that is the differential equation that describes the behavior of the system, has the following form: K2 C to the second power, where K2 is the rate constant of the second order reaction. We can easily integrate this equation. In other words, we can easily find the functions that are solutions of this differential equation by the method of separation of variables. We move on the left side the dependent variable, while on the right side we move the independent variable. And of course, we can integrate both sides, and we obtain 1 over c equals K2 times t plus a constant, which is to be determined. It is obvious that at the beginning of the reaction, that is at time t equals to 0, this expression will have the following form: 1 over c0 equals 0 plus constant. In this way, we see that the value of this arbitrary constant is equal to 1 over C0. Thus, for second order reactions, for which the initial concentrations of the reactants are equal to each other, the reciprocal value of the concentration of the reactant is a linear function of time. Here, the second order rate constant is the slope of this line, and the reciprocal of the initial concentration is the intercept. The solution of the differential equation can be rearranged to express the second order reaction constant. These are the units of the second order reaction constant. It is easy now to obtain the half-life of the second order reaction by replacing in this expression of the half initial concentration. We can transfer this term on the left side of the equation. 1/2. And of course, we can rewrite this, which in fact is equal to this expression from where the half-life is equal to 1 over C0 K2. Now we see that unlike the first order reactions, the half-life of the second order reaction depends on the initial concentration of the reactant. If the initial concentrations of the reactants in the second order reaction are not the same, then the differential equation that describes this type of situation is as follows. Where A and B denote the initial concentrations of the reactants, while X is the concentration of the species that have already reacted. We can separate the variables in this differential equation, and to make it simpler for integration, we can rearrange it in this way, and then we can integrate both sides. We take this in front of the integral because it's a constant. The integration leads to this expression, respectively this one, which contains an arbitrary constant. At time t0, the expression attains this form, from where the value of the constant can be determined. Thus, the constant is equal to this expression, which we can substitute in the solution of the differential equation, from where the second order rate constant is obtained in the case when the initial concentrations of the reactants are not the same. As is seen, in this case, the second order rate constant is expressed again in liters per mole per second. Here are some examples of second order reactions. These are saponification of esters with alkali. This is ethyl acetate, and this is isopropyl acetate. This is a brief summary of the discussed so far. In this summary, we have arranged matters so that linear dependencies are obtained between the parameters in the different orders of reactions. Linear dependencies are the simplest to understand and are preferable to use when analyzing data. Thus, if as a result of an experiment it has been found that there is a linear dependence between the concentration of the reactant and time, then the conclusion is that the reaction is a zeroth order. On the other hand, if it has been found that the linear dependence is between the logarithm of the concentration of the reactant and time, then most likely this reaction is a first order. Here we see the slopes of these lines are negative. And finally, if the linear dependence is between the reciprocal value of the concentration of the reactant and time, then the conclusion is that the reaction is a second order. Here's another interesting thing to note. If we want to compare the rates of first and second order reactions, it is not possible to use the rate constants of these reactions, because as we saw, they are measured in different units. We can, however, use the half-life of the reactions. Here, the concentration time curves of two hypothetical reactions, one of first and the other of second order, are presented, which happen to have the same value of half-life. It is seen that for times less than one half-life, the run of these two curves is quite similar, and it is difficult to discern which one is of first and which of second order. However, for times greater than one half-life, the run of the curves diverges, and the concentration of the species undergoing first order reaction tends towards zero much faster than the concentration of the species undergoing second order reaction. Indeed, as we already know, unlike the first order reactions, the half-life of second order reactions depends on the initial concentration of the reactant. This dependence is such that for second order reactions, the lower the starting concentration, the greater the half-life. Therefore, for second order reactions, it will take longer for the concentration to decrease to zero. This is easy to understand physically. While the species undergoing first order reaction do it by themselves and are always available, their reacting will be faster than the reactions between species that have to reach each other, and as the time goes by, there are fewer and fewer species to meet.